Alright, here we go with iChem lesson 16, our first one of this new unit 5. We're going to spend some time on defining and doing calculations using the mole. We touched upon it in class today, and now we're going to kind of put some definitions and some steps and procedures down on paper. So first of all, you don't really need to write anything on this slide. It's just kind of like a primer relating to what we were doing in class today. So it's a metric base unit. It can be defined in 3 different ways. We'll talk about how you define it based on mass, number of molecules, and volume of a gas. It represents a very specific number in the same way that a dozen represents 12 and a pair represents 2. A mole represents 6.02 times 10 to the 23rd, which is a very large number because atoms are very small. So it creates sort of a measurement of number of atoms in a way that makes sense to everyday life. So 1 mole is equal to 6.02 times 10 to the 23rd. This number is called Avogadro's number. So Avogadro's number is 6.02 times 10 to the 23rd. The first idea we need to define related to this is molar mass. It's the mass of 1 mole of any type of like items. So the molar mass of an element is just the mass of the element you find on the periodic table. And the molar mass of a compound is a sum of all the elemental molar masses. So if we take a look at our periodic table, we can come up with the molar mass for all of these examples here. Copper, well, copper is just an element on the periodic table, so I find copper and I copy down its molar mass. And the units, grams per mole. Okay, so the same number AMU, atomic mass units, we're using for grams per mole now, and we can do that because of the way the mole is defined. Now oxygen, you can kind of go 2 different ways. If this is the oxygen atom, I would put it straight from the periodic table. But oxygen, remember, is diatomic. So if I'm talking about oxygen as just the elemental compound, it's going to be O2, which means I have 2 of them, 2 times the number on the periodic table, which is 15.9994, which is why you see I always write it as just 16. You can round a lot of these. Especially if it's 0.9994, we could have called that just 16. So 2 times 16 equals 32 grams per mole. Now carbon dioxide, we got to write the formula. And now we can see that formula writing is still very important, because if we don't have the right formula, we can't combine the masses in the right way, and we won't end up with the correct molar mass. So let's do carbon dioxide. We're adding up for each of the elements. So I think it helps. I have carbon and I have oxygen. I have 1 carbon and I have 2 oxygen. Carbon's molar mass from the periodic table is 12.0107, and oxygen's is 15.9994, which we could easily just call 16, and we probably will from this point forward. This gives us 44 grams per mole. Alright, last one, iron 3 sulfate. Well, first we have to write the formula. It's ionic, so I'm starting from my ions. The 3 tells me the charge on iron. I swap and drop, I get Fe2SO4 3. Alright, now I have to add all of these up. Let me come over here. I have now iron, sulfur, and oxygen. I have to add them all up separately because I find them separately on the periodic table with their masses. I have 2 irons. I have, careful here with the parentheses, I have 3 sulfurs, and I have 12 oxygens. So iron's molar mass is found on the periodic table, 55.85, sulfurs 32.06, and oxygen I'm just going to call 16. So I pull up my calculator and add all of these together. I get 55.85 plus, or times 2, sorry, times 2 plus 32.06 times 3 plus 16 times 12. I get a molar mass of 399 grams per mole. Alright, now we can build on this and define the mole. The mole can be defined by counting particles in a sample, weighing a sample, or measuring the volume. So we call this thing the mole map. Count particles, we're down here on the mole map. If we have mass, we're over here on the mole map. If we have volume, we're over here. And there, you can see on your map, you have these things called conversion factors. I'm going to talk about how to use them on the next slide. So, first of all, the conversion factor, if you have particles and you want moles, or you have moles and you want particles, the conversion factor is Avogadro's number. With this equality, remember for unit conversions in the past, we use unit equalities to create ratios. This equality here is 1 mole is 6.02 times 10 to the 23rd, and that could be particles, atoms, molecules, formula units, and so on. Mass, the conversion factor is molar mass, and we just learned how to figure that out. If it's an element, it comes directly from the periodic table. If it's a compound, it comes from adding up the elements on the periodic table. And finally, lesser used but still important is volume. It's only volume of a gas we can convert, where 1 mole equals 22.4 liters per volume of a gas. So as you go towards the mole, so from particles to moles, or from volume to gas, you divide by the conversion factor. So if I had a number of particles and I wanted to figure out moles, I would divide by the conversion factor. As I go away from the mole in the diagram, so from moles to particles, I would multiply by that conversion factor, Avogadro's number. Now, I prefer, instead of you memorizing, go towards, divide, and move away, multiply, to do it the same way we were doing at the very beginning of this semester with our dimensional analysis. So let's do an example like that. So aluminum is often used for structures such as high-quality bicycle frames. And we're interested in the number of moles in a 10-gram sample. So let's just kind of see where we are. 10 grams, that's a unit of mass. So we're here, and we want to go to moles. So let me just write what I have to start with. I have 10.0 grams. The conversion factor I have here is 1 mole equals blank grams, and the number that goes here is my molar mass. So for aluminum, if I look on the periodic table, I find the molar mass to be 26.98. Okay, so 1 mole for aluminum equals 26.98 grams. You remember, if I set up dimensional analysis, I take the unit that's here and I put it in the bottom. And I take the unit I want and I put it on top. And now the numbers in my equality are what go in here. So 1 mole, 26.98 grams. If I plug that into my calculator, I end up with 0.3706 moles, and then specifically of aluminum, moles of AF. Alright, let's do another example. If we have moles now, 0.5 moles, and we want to know how many atoms, so moles to particles, atoms. My conversion factor is Avogadro's number. Okay, now I write what I'm starting with, 0.5 moles. Moles, if I'm converting from it, should go in the opposite corner. And I want atoms. Okay, and we're talking about something that is just an atom in both ways. So moles to atoms would just be 1 mole here and 6.02 times 10 to the 23rd atoms. If I plug this into my calculator, I get 3.01 times 10 to the 23rd atoms. And let's be specific in our answer, of magnesium. Alright, let's do another one. We have a volume of gas given. Oh no, sorry. We have moles given, and we want volume of gas. So a cell releases 0.25 moles of O2 gas. What volume would be needed to hold this gas? So my conversion factor, 1 mole is 22.4 liters. If I start with my given, 0.25 moles, I'm converting from moles, so it goes in the opposite corner. And I want volume, so that on top, now fill in with your equality, 1 mole, 22.4 liters. Now plug this into your calculator, 0.25 times 22.4, you get 5.6 liters of oxygen, liters O2. Okay, I have one more, and this is going to be a multi-step problem. So this time, you want the number of formula units, that's where my destination is, from mass. So now I have two I can't go, there's no path directly here, so I have to go from mass to moles, and then from moles to particles. That's 2 unit equalities. I'm starting with 45.0 grams. Take what I'm starting with, goes in the bottom corner. Now, grams, I can only go directly to moles, so that's where I'm going. Now I have moles in the top corner, putting moles down here. From moles to particles, or formula units. Formula units is just another way of saying molecules, but for ionic compounds. Formula units. Okay, so now I have the structure, I can fill in the numbers. So for here, I'm coming to my unit equality, and this is iron oxide. I need the molar mass. So I have FeO, 1 iron, 1 oxygen. So 55.85, that came from the periodic table, plus 16. Now I need to add this up. 55.85 plus 16. Got 71.85. So that's my conversion factor here. Grams per mole. Grams per mole. 71.85. 1 mole. So now my grams is canceled.